Welcome to the Picture Language Seminar. We're very happy to have David Ruelle this morning. David is actually sitting next to me in my office. 2 days ago, he presented the David Lee Historical Lecture here at Harvard. And it's wonderful to have this icon of mathematical physics talk in our Picture Language Seminar. David's worked in so many different fields, from quantum field theory to statistical physics to dynamical systems, and made seminal progress in every one. So we're looking forward to his overview today on a natural limitation for proper human scientific progress. I'm going to let David sit here and get out of the picture, and look forward very much to hearing your talk. So I set this up.
Hello. So I would like to talk about natural limitation for properly human scientific progress. And in a sense, this will be very short. Namely, this is a philosophical problem, and I claim that scientists have a right to look into the problems related to their work. These are scientific problems. However, I do not think this is a good idea to follow the philosophical tradition and the published literature in philosophy. In fact, let me mention a couple of scientific quotes from scientists and, in fact, mathematicians about philosophy. When a philosopher says something that is true, then it is trivial. When he says something that is not trivial, then it's false. This is Gauss. And Whitehead said the safest general characterization of the European philosophical tradition is that it consists of a series of footnotes to Plato. Now, I will nevertheless mention some articles about the philosophy of science. They are given below, and you are welcome to use these references. But I think I would like to forget about the traditional philosophy and think that I have the right to think about myself, about my own work, without feeling obliged to follow the philosophical tradition. Now, the idea to follow, to be interested in one's own scientific work and to discuss it is illustrated by an article by Jeffy and Quinn, which is, I think, a good example of what one can do. And I also wrote a paper which is not published and which is philosophical philosophical thinking about post-human mathematics. Now, as to the limitation of human of human scientific progress, I shall be very quick, namely about scientific but not mathematical progress. I have little to say. Science progresses, but I cannot say very much at which rate it does progress. As for mathematical progress, then Gödel has obtained some results which say that essentially the length of proofs of mathematical theorem grows very, very fast. This is a fact of the mathematical logics, and I will not try to prove this, but simply it's a fact that means that the rate of progress per mathematician should decrease with time. So that's in fact the whole story, and I will not go beyond that, except one question. And the question that I would like to consider is, what is the nature of human mathematics? Now, mathematics is, in fact, the series of results of axioms of mathematics, the Zermelo-Fraenkel and Choice axioms. And one can consider that all the consequences of Zermelo-Fraenkel choice are, in fact, the whole of mathematics. One can make other choices of axioms, but these are the usual ones. And as I have mentioned, there are very long proofs, which is something which is related to the Gödel incompleteness theorem. And for instance, Turing has shown the undecidability of the halting problem for Turing machines, which means that there are some very long proofs, and that reproves my claim that the contribution of individual mathematicians will decrease with time. Now, however, human mathematical work is based on structures, namely Euclidean space, groups, compact spaces, etc. And the structure of human mathematics is based on these structures. So the work of Bourbaki, Grothendieck, and so on is based on these structures. And we see structures, for instance, when we look into, if we compare two equations, one is 3 to the squared plus 4 to the squared equal 5 to the squared, which is a well-known equation. And it means to most mathematicians that there is a right angle triangle which has hypotenuse 5 and the sides of the right angle have length 3 and 4. Now, there is another statement, which is 3 to the cube plus 4 to the cube plus 5 to the cube is equal to 6 to the cube. That's easily verified. And in fact, I mentioned this to Deligne, and he knew this fact. Nevertheless, it's not part of standard mathematics. It seems to be an accident. And to my knowledge, it's not part of essential mathematics. Okay. Doesn't seem to go on. Oh, okay, very good. It doesn't.
Right. Okay.
Voilà. Okay, so let's try to think about human mathematics. Human mathematics is not all consequences of the axioms, but some consequences that make sense. And this relates to the human brain. And that is part of philosophy. But I think I want to think about this part of philosophy in my own terms and not follow the philosophers. In fact, I wrote a book on mathematics, which was reviewed by a philosopher, and he claimed that this was, he made a somewhat negative assessment of this book, saying that I did not quote, that this was philosophy, and I did not quote philosophers. I think I want to stay with this. Okay, so the problem with philosophy is that it uses concepts which are non-scientific, like consciousness, truth. Of course, truth has some scientific meaning, but the concept, the philosophical concepts are generally not related to science. And so I would consider the the philosophical concepts on their own value and not accept them as such. Now, there is I would like to talk about mathematics as seen by mathematicians. And mathematicians have said quite a bit of stuff about mathematics. For instance, there is a great diversity of intellectual profiles of mathematicians. For instance, in the early 20th century, Poincaré, Hilbert, Gödel, and von Neumann have very different individual features. And this is different from the speed at which human racing speed can be limited. For instance, Usain Bolt, who is the fastest man on the surface of the Earth, reached a speed of 44.72 kilometers per hour, very briefly. And there are animals that go twice as fast. So this diversity of speed of animals can be explained by an evolutionary argument. Humans to survive have to have a certain speed, but there are other elements, and that means that the human speed is rather limited to a given value, while the profiles of mathematicians have not been acted upon by human evolution, not for a very long time, and therefore there is a great diversity of things, of mathematical, by humans. Now, human proofs are understandable by humans, and the concept of understanding is a philosophical concept. It is related to the functioning of the human brain, and therefore it is not easy to define in a scientific way. So since we are going to discuss human mathematics, we do refer to philosophical concepts, and I want to insist on the fact that one has to be very prudent in using such concepts. Now, one can, however, compare the human brain, which does human mathematics, with other sources of mathematical knowledge. So what can we do? What can we say about human functioning as used in mathematics? The human brain is slow and prone to error and has a limited memory, and it is also highly parallel. So the fact is that these features of the human brain, which are mostly somewhat negative, slow, prone to error, limited memory, nevertheless have a possibility to create mathematics which computers cannot match at this moment. I believe that in due time there will be mathematics created by computers, and it would be very interesting to see how different this will be from human mathematics. But human mathematics, and I'm excluding the use of computers at this moment. So human mathematics is a rather special set of results from the mathematical axioms. So mathematicians have thought about their own work, and this is philosophical thinking, but I'm referring to the ideas of mathematicians rather than the ideas of philosophers. Gauss, Poincaré, Hadamard, Artic, and so on have written about mathematical thinking, and they have insisted on the role of several features of the human thinking. One is the role of unconscious thinking. This is somewhat limited remark, because we do not know how unconscious thinking works, but the fact is that it contributes to human mathematical discovery. Another feature of the human brain is that it has short-term memory. There is a working memory which extends to like 7 items. This is what is considered the working memory. And this means that thinking usually involves a small number of items in the working memory, and these are submitted to combinatorial features of thinking, and therefore that shows that the human mathematics will be limited to concepts which have a name. So short.
You've gone away again.
Sorry?
No, this
It's okay. Since we have short-term memory, it's good for us to introduce concepts which have a name, and we can work with like 7 concepts with such a name, while a computer could work with concepts which are like 10,000 words, and for instance, immediately see if one concept and another concept are equivalent in the sense that they contain the same number of words, the same words, which would be very difficult for a human to do. So the human brain works differently from a computer, and in has a limit that it must use short. It must use concepts which can be expressed by a short word. And
David, if you couple several mathematicians together, the short-term memory bound can increase.
Klaus said that if you put two mathematicians together, the short-term memory can increase.
well, no, I mean, one can increase the short-term memory by using names. I mean, the thinking is done by an individual, and the individual can use results proved by other individuals, but the proper working is by an individual mathematician. So there is collective growth of mathematics due to the fact that several mathematicians work in a collaborative manner, but the individual result given what is known in mathematics at a given time, this is done by an individual. At least that's how I see things. So we have some features of the work of the human brain in mathematics, but this does not amount to a theory of mathematical creativity. If we had such a theory, it would be possible to work out a program of computer that would create mathematics, and creation of mathematics is very limited. I mean, what can be done is to tell a computer to verify a certain number of things, which it can do very fast, but it is not the creative part of the use of computers is done at this moment by humans. Okay, so human mathematics is not, has changed with time, since there is a vast domain of possibility. You can name new domains, like we can, the computational complexity is something that has been introduced after computers were introduced, and the question of NP completeness is a new part of mathematics. Now, short-term memory leads to the definition of structures, which also vary with time, namely the concepts of Euclidean geometry are extremely old by human standards, 2000 years, but the concept of group is something relatively recent, and it's relatively recently that one has introduced systematically different mathematical structures. Now, human mathematics is understandable by humans, and human understanding does not function in a formal language. Mathematical statements can be translated into formal language, after which they become very difficult to understand. Now, as I have mentioned already, understanding is part of the philosophical basis of the human nature, and it is to be treated with great, I mean, it is not something that can be well understood. Understanding is not well understood. It's a fact. No, so as I have mentioned repeatedly, the human mathematics is different from the set of provable theorems for the axioms. It's completely possible that there is an extremely important theorem which shortest formulation involves 1 million pages of mathematical text, in which case we are unable to understand this problem. Although it may be that consequences of the theorem in question can be understood, but this is something different. So the fact is that human mathematics is different from the set of consequences of the atoms, but it's limited by the Gödel theorem that proofs of individual results must be extremely, the proof of some individual results must be extremely long, and that applies to human mathematics as well, and therefore the progress of individual mathematicians should decrease with time. Now, let's you what happened?
I muted him. He was talking to somebody at his house.
Oh, okay. Sorry. So Klaus, you don't say anything at this point. Okay. So let me sort of review the creative human mathematical thinking. Human understandable jargon is based on natural language. It may be French, it may be English, or it may be ancient Greek, but it's often in written form, and it is using natural language. It's possible to translate this human language into axiom-based formalized language, but this becomes then very hard to understand, and it's usually not done. There is an exception in the sense that human proofs are translated to machine readable proofs that can check for exactness of result. So human mathematics, since it's based on the functioning of the human brain, is prone to errors. And the fact that there are very long proofs, like several thousand pages, means that errors can creep in very easily. And therefore, the one use of computer has become important, and this is to check that proofs are correct. This means quite a bit of work translating human mathematics to a set of lemmas which can be verified by computers, but it's important now. Now, properly human mathematics, of which I've sort of insisted that it would decrease, that the production of an individual mathematician would decrease with time, does not include things that use computers in an essential way. For instance, Hale's proof of Kepler's conjecture on the packing of spheres is essential use of computers, although it's based on human mathematical thinking. But it means that there is an acceleration of the speed of production of mathematics by individual mathematicians if they use a computer. Now, there's an interesting problem, which is that human mathematics is based on structures, and these structures are time-dependent introductions. And some people, like Bourbaki and Grothendieck and so on, think that mathematics, they don't say human mathematics, but they refer obviously to human mathematics, that mathematics is essentially structural. If one looks at the axioms of mathematics, there is no structure that is obvious in these axioms. So the structural features of mathematics are introduced by human mathematicians, and some mathematicians believe that they have discovered the natural structures of mathematics. So Bourbaki has a series of volumes, unfinished actually, which refer to set theory, algebra, and other branches of mathematics. It's not at all clear that a structural understanding of mathematics is actually natural. So let me summarize. Human mathematics is based on axioms, and human mathematics uses natural language plus jargon, which can be translated into formal language, but is not usually translated into formal language because of short-term working memory and trying to avoid errors. We use short formulations, which are sequences of sentences in a human-based language, and we name concepts, and that's how mathematics actually, that's how human mathematics actually functions. And mathematical thinking is combinatorial and partly unconscious, and it is creative, but we don't know at this point how it works because we don't know how the brain functions. So purely human mathematics is different, as I have said again and again, from a set of consequences of the axioms. Let me briefly say something about non-mathematical science, and I have very little to say. I mean, scientific theory is a piece of reality which is identified with a mathematical structure. But there are various ingredients to the rate of scientific progress. For instance, political decisions. There was a decision in 1993 not to build a superconducting super collider, and that changed the evolution of physics. There is also Moore's law, which is the fact that the number of transistors in an integrated circuit doubles every year, and that is a fact that influences the rate of growth of science. And the fact is that I will therefore not make any general statement about the rate of growth of non-mathematical science. I'll stop there.
Well, thank you very much, David, for a really interesting talk. And I'll stop the screen sharing so we can see each other and hopefully generate a very interesting discussion. I see there are many people from broad domains here. When you talk, I hope you'll turn on your video so we can see your face. Who would like to start the discussion? Nikita.
Close.
Oh, Klaus.
Okay, Klaus, go ahead. Yes. Klaus is muted.
And then get
Okay, I think in the applied sciences, at least, and neuroscience, for instance, is an example. There is a general congestion. The number of the data are growing so fast that no human brain can actually see through them. And it is getting worse and worse. And I think there's a natural stopping of research in experimental biology because we can't cope with the enormous amount of data and data on data and so on.
so that's a statement about
That's a statement, yes. A natural limit will be congestion.
yeah, okay. But I mean, there may be some structure. After all, the brain is self-organized on the basis of a long set of bases in the genome, but it's not infinitely long. In fact, it's somewhat limited, and therefore there must be some there could be some understanding of the structure of human thinking that follows from this self-organization. I mean, I'm not saying that we know this at this time, but there is a possibility of progress.
So Nikita, did you want to comment?
Yes, I wanted to ask, David, do you think that consciousness can ever become a scientific concept?
Okay, I think consciousness is a complex phenomenon. I think when we know more about the functioning of the brain, we may be able to correlate consciousness with some features of the brain function. What I'm objecting to philosophers is that they tend to start with consciousness. Je pense, donc je suis. Cogito ergo sum. And that's, in my opinion, a very poor way of, I mean, it may be convincing. We are convinced that we exist. What it means that we exist is not at all clear. What it means that we think is also not very clear. And proving the existence of God by this sort of arguing is, in my opinion, very unconvincing. I mean, I have a Catholic wife, and I don't object to people believing in God. I think simply a scientific proof of the existence of God is no longer considered a reasonable thing.
No, of course, but what steps could we make towards understanding the nature of consciousness? So, for example, is mathematical thinking, is it a model of thinking itself, or is it something completely new?
Okay, well, the fact that we can create mathematics is a feature of the functioning of the brain. So that means that we have a brain that can do something of which we have some idea intuitively, but it does not mean that by thinking of how we do mathematics, we can understand the functioning of the brain. I think that's not the case.
So Jörg, do you have a comment?
I have a question. Is mathematics a creation of the human mind, or is it something that is intrinsically already there in reality, and we just, happen to find it as we sort of perceive reality? It's the contingent question. What's your take on that?
Okay, well, I mean,
East versus West.
the concept of existence is one a questionable concept.
Yeah.
Logical existence is one thing, and it has been proved by Gödel that we cannot really be sure that there's a consistent existence of mathematics, but we can believe that this is the case, in which case one can speak of existence. But I mean, I do believe that there is a logical existence of mathematics. In fact, the axioms of set theory are very natural axioms, and it's difficult to not believe them. Apart from the axiom of choice, which is somewhat special, but has been shown to be consistent with the other axioms, which are more believable. So I think mathematics is, if anything is believable, more the most believable thing. Now, also experimental sciences. I mean, if you take sulfur and heat it, and it melts, and then you put the molten sulfur into water, it gives something that is like rubber and brownish. And that's a fact, an experimental fact of science, which we can try to understand. After a while, it becomes yellow and ordinary sulfur. But so, I mean, we have some understanding of the outside world, and it exists in some sense. In what sense exactly, from a philosophical point of view, that's disputable, but certainly things remain, there's some sort of consistency of the physical world. And this is one great discovery that's foundational for science. Science does exist because there is some consistency of the physical world as we see it.
So sometimes, David, I have difficulty in explaining with physicists the difference between a mathematical proof and a physics argument. And when I talked about the paper with Quinn, with Jean-Pierre Serre, he's remarked that practically every mathematical paper he wrote, he found a mistake in it. It's a small mistake, correctable, but a mistake.
Yeah. So that's one thing. I mean, some mathematical results have stayed for sufficiently long time that we do believe in them. However, errors in long proofs are a problem which has been attacked by using computers.
But it's a very difficult problem to check things by computer. In fact, we don't really know yet how to do that.
I think checking by computer, I mean, it's a complicated thing, but it is quite convincing. The result is very convincing. So computer checked proofs are really quite believable. Michael Douglas.
I think you're muted, Mike.
Hello. Yes. I know. Am I muted now?
We can hear you now.
Okay. Yeah. Thanks. Very nice talk. Very stimulating. Yeah. I mean, a lot of progress is being made on computer proof, on AI to help make computer proof more automatic. I mean, in terms of its relevance for mathematics, there's this recent what's called liquid tensor experiment of verifying work of Peter Schulze, which you can look up on the web. That's very interesting. There's a number of AI researchers that are using AI to at least more automate these proof systems, which is very laborious right now, not nearly as much as it was, say, even 10 years ago when Hales was making his proof, but still laborious. But it becomes, the computer does more and more of the work. And then, again, many people in AI think that it's just a matter of time, before there's a computer that rivals or perhaps even exceeds the human intelligence. So let me just throw out one broad question of the sort that you were asking, which is the question of whether to make a computer do what we would call mathematics, to prove some type that we find interesting, that we can understand. Is that going to turn out to be the same problem as creating a general intelligence, or is it a different or perhaps easier problem? So in other words, if the computer could be made to do mathematics, would it, by the same virtue or very quickly, also be able to do all the other tasks that we consider intelligence? Or is this a problem with some difference, so that it would be good in mathematics and not necessarily good at all of human intelligence? So it's an interesting question. And
It's just the question of
I think that's the big question. Of course, you can put a program which will try to do something like human mathematics, or maybe you cannot do that. It's unclear. What Gödel's result about very long proof means is that there may be logically true statements which are somewhat inaccessible, or maybe accessible by computers, but not really by us. I mean, we tend to think of men as the center of the universe. I have the notion that maybe all of our human understanding is little as compared to the understanding of some non-human beings on some distant planets. I mean, that means that one should be somewhat modest about human science. I mean, it's a good occupation, especially it has been for me. But the fact is that it may not be as central to the universe as we tend to think.
Okay, yes. Thanks.
Are there other comments?
Clemens?
Can I go next?
Yes, Van.
Yeah. So you mentioned Vygotsky in one of your slides. So the new way of founding mathematics, all this univalence foundation, which Vygotsky started. So they are coming up with the new foundations, probably every couple of years. So each one of the foundation of mathematics, if you apply the Gödel's theorem, it might miss out some facts, but it will capture other facts. But if you consider a bunch of these foundations of mathematics, then they might be able to close all the gaps. Then they may become equivalent to human creativity. So what do you think of that possibility?
Okay, so there are superstructures on mathematics which have been introduced and go beyond the axioms of, the basic axioms of set theory.
Mm-hmm.
So it may be possible to prove some theorems even about traditional mathematics, which are inaccessible. But this is a very interesting idea. Of course, results obtained using new concepts will naturally occur. So I think the fact is that the basic axioms of set theory have controlled mathematics for a couple of centuries, but they may not go, this may not go on forever. However, the basis that one looks at the set of axioms, that is 2000 years old, and that has been a very productive idea. So I don't know if I answer your question, but
yeah, but I mean, thanks for the perspective. Yeah, I get it. Yeah.
So I see a raised hand, but I can't see.
Yeah.
Hi.
Hi.
Yeah. Hi. Thank you very much for a nice talk, David. I have a little question. You talked mostly about mathematics itself. If I ask the question, how much more do you think we can learn about the complexities of the physical world using human mathematics only?
Well, I think the human mathematics is probably quite adequate. I mean, the problem is to understand the physical structure, and that means introducing philosophy, physical concepts, and looking at I mean, looking at good notions to understand the physical world. I mean, there are all kinds of problems like the fundamental problem of the structure of elementary particles, and that's one thing. But then there are complex systems which have all kinds of different features which have to be investigated case by case. I don't think the limitation would be mathematical, although mathematical invention may be appropriate to understand some problems, but it's nothing so fundamental. I mean, I think the fundamental features of mathematics would not be essential to understand the fundamental features of the physics.
Did you have another comment?
Thank you.
I have another question. What is the nature of the algorithms that our brains use when they do mathematical operations or when they think about the proof or so? Is there any element of quantum algorithms involved? For example, when some kind of human being can compute whether the 8th of September 1894 was a Thursday or a Friday. What's the algorithm that is at work? Is that understood?
I'm completely incapable of doing so. I know there are people who are able to do these calculations. Now, as for the importance of quantum mechanics, I heard Klaus Hepp saying that it was not important. So that's my source of information.
Yeah. The decoherence is so fast that the algorithms which we are using in doing mathematics are of orders of magnitude more prolonged than what quantum effects take place. Of course, we have macroscopic quantum systems like superconductors or so, but there's no evidence that the brain is working on at the level of superconducting.
So that's your answer.
Arthur, do you have a question?
Yeah, I think it's along these lines of this quantum direction, but when we do mathematics and what we call natural, or when we think about natural axioms or something that we just call natural, is usually motivated by our experience, which is in itself rooted in our classical experience, our experience with the classical world, at least the way that mathematics was developed over the centuries. And so, you would think that natural, what meant natural a long time ago was something that was really defined in terms of reproducing classical physics, classical reality. But wouldn't it be more natural to sort of rethink about how, what we consider axioms as if we were quantum mechanical beings? We can't really think about that, but if mathematics was discovered by quantum particles, would it look much different than it does as discovered by humans?
I think not. I mean, the axioms of set theory are things like there exists an infinite set. I mean, what is classical or quantum about that is unclear. So I think the axioms of set theory are generally believable, and I don't think classical or quantum physics plays any role. Of course, the orientation in which mathematics develops is influenced by the fact. In fact, I am impressed by the fact that some people think quantum mechanically, and I'm thinking mostly classically, but I can understand that a quantum understanding of nature may be quite natural to some people. But I don't think this has anything to do with the basis of mathematics.
Does anybody else want to make a comment or ask a question? Well, if not, I'd like to thank David again for an absolutely fascinating talk. Welcome you back next Tuesday for our next meeting. Bye-bye. Bye-bye.
Thank you, David.
Thank you.
Bye-bye.